Today, Kurt Marlin will explain how the ComSoft platform provides comprehensive insights into the design and the deployment of heat networks in a city centre context. Once Kurt is finished, we will kick off the Q&A and also address any questions you may have. So for those of you unfamiliar, you should find a question box there. You can stick your questions in at any time over the course of the presentation, and I'll do my best to pick out the questions and put them to the panel. So yeah, just put them all there. We really appreciate any points of view and questions and thoughts coming through. So yeah, this morning I'd like to introduce Heat Vision 2030. Heat Vision 2030 is about demonstrating that the technology, systems, methodologies, commercial partners and models are ready and available to design, specify, procure, roll out, finance, operate, optimize and maintain a heat network for Glasgow and indeed cities here in the UK and abroad. This project began by asking the question, how can we deliver a zero carbon heat network for Glasgow City Centre by 2030? In light of Glasgow City's declaration of trying to become net zero by 2030. And this question inspired us to develop an ambitious, exciting and realistic vision of supplying Glasgow City Centre with zero carbon heat. A vision that might galvanise the city, its citizens, the business community, community groups, and the political establishment to act quickly and boldly in the face of our climate crisis. It is a work in progress, and it is out of our conviction and our vocation to try and deliver heat networks. So it's there to be looked at, analysed, criticised, and developed. That's really a part of the whole philosophy. So today is part of that process where we demonstrate that our goal is eminently achievable. Kurt will now present the first tranche of our work as visualized by the ComSoft software, including a detailed map of the heat network rollout, initial estimates of total heat demand and total heat supply, outline costs of deploying the heat network, and yeah, amongst lots of other interesting information. Over to you, Kurt. I'll turn off my webcam if you turn on yours, and yeah, good stuff. Listen, over to you, Kurt, and look forward to it.
Okay, well, thank you very much, Ben. Let's see if I can switch to the next slide. I don't seem to have controls yet. Right, okay, here we go.
You have control now, Kurt.
That was too fast. Sorry about this one. Okay, here we go. Well, good morning, everybody. The city we're going to look at today is Glasgow. Glasgow has developed an energy and carbon master plan a while ago, and one of the main actions in the plan are the development of new district heating schemes in the city. Currently, there are about 3 district heating schemes, and these will be expanded, or additional district heating networks will be added in the city. So the area we're considering today is the city centre. So basically the part north of the River Clyde is centred around the main train station. And this area has about 1,000 buildings, big buildings requiring a lot of heat. So we're going to look at this area, and we want to know information such as the network deployment cost. We're going to look at the source power requirements. We're going to see what could be the possible rollout scenarios, and also we want to look at the economical feasibility over a period of 40 years. So as Ben mentioned, ComSoft has developed a planning tool, a planning and design tool, ComSoft Heat, which is a GIS-based automated planning and design software for district heating networks. And currently, most of the projects which are being done with the software are used as inputs for business cases, feasibility studies, and it speeds up the planning process. It provides you different tools and outputs to get all the information you need in this stage of the process. So how does a tool work? Basically, we start from the area. So we need to know the GIS information of the area under consideration, the building information, street information, and heat demand information, of course. In the next step, we will add the technical design parameters, pressure, temperature, type of pipes that will be used, information about the heat delivery units, information about the source. And this is then the input for the design. All right. Once the information is available, the tool will start calculating the network and provide a network design. So we see here on the right side the same area, but now we have generated different clusters. So each cluster is a group of buildings interconnected to a source or interconnected to a substation. And within those clusters, the pipes have been routed automatically. The pipes have been sized according to the heat demand that is required for the buildings. And additionally, the deployment cost calculation will be calculated for the network under consideration. So I'm now going to look to the principles now that we have applied for Glasgow based on this methodology. So first of all, the first step is the GIS data. So we need to have a good source of GIS data. We can buy commercial data, so from commercial companies providing GIS databases. That's one of the options. Mostly local authorities, they have good GIS data as well of their city. That's a second option. But in this case, we have used open data sources. OpenStreetMap has been used as a source now for this exercise. And we need, as mentioned, building information and road information to start. A second very important parameter for the design, of course, is the energy consumption per building. So there are different sources again. The most accurate source would be getting the data from the gas utility company. But for reasons of privacy, this is usually not possible. And this information is not shared with network designers, consulting companies. So that's a difficult part to get to this data. Another approach would be to do a survey and approach the individual building owners to get to know exactly what is the energy consumption for their building. That could be done, let's say, in a further stage of the project, but at this moment in time, in the feasibility study phase, this is too time-consuming and also too expensive to do at this point in time. So the third model is what we have applied here. So we have based the data on building type, building age, level of insulation, number of floors, etc. This kind of information to estimate the heat demand. And all this information has been gathered in an online database in the Hot Maps project. So the Hot Maps project is an European project. A project that has been funded by the European Union, executed by multiple universities and European companies. And the data is online available, and that means that there is data available for the main cities in Europe. So we have applied this for Glasgow. So you see here the map of Glasgow in the online tool of Hot Maps. You can select the area, and it will give you the heat density information for that specific area. There is different layers of detail. So we took here the highest level of detail. So then we can map this layer on top of our GIS data and assign the heat density information to the different buildings in the area to get an estimate of the heat demand. So when we look specifically for the case of Glasgow, the hot maps database gives us that there is a total energy demand per year of 200 gigawatt hours. And the gross floor area is 1.6 million square meters. So we have to take those into account to distribute now the energy demand over the different buildings in the area. So we have used this as a source for the energy consumption. Another question is where will we get the energy from? So the company Star Renewable Energy, they have a solution and by means of a big river source heat pumps, which can be used as an energy source. So these heat pumps, they can supply water with a temperature of 80 degrees or higher. And the idea would be to cascade multiple units of 5 megawatt peak. And based on measurements of the daily flow in the river, it can be calculated that the river can support more than 200 megawatt peak. So that should certainly be enough for this area. Now, how does Minibems come into the picture here? Minibems has a network control system which monitors the network conditions at all times, and they can guarantee that the return temperatures will be as low as possible, and it will also control the network operating flow. Why is this important? Because when we design a district heating network, we have to assume a certain delta T, so we have a supply temperature, but also very important is to have a good certainty about the return temperatures. So by using the Minibems control system on top of the network, we can assume during the design stage that we can have a solid return temperature. So we will assume in the design a delta T of 30 degrees, which can be maintained. So to go back to the area, so we see there in the south of the area where you see the star positioned, that will be the source location. We're going to work with a single source, so with a supply temperature of 80 degrees and a delta T of 30 degrees for this first scenario. So this is then a first design generated by Comsoft Heat, and we're now looking only at the transport network. So this is a transport network, kind of a backbone network to route the energy from the river source to different substations in the city center. So this backbone network has a length of about 7.5 kilometers, and each backbone station will serve a group of buildings. Here, the clusters that you're seeing, these are showing which group of buildings are belonging to the different substations. And again, here, all the clustering, all the routing, pipe sizing has been fully automated, so by Comsoft Heat. So basically, once your project has been set up, which takes you here for this area, let's say about half a day, you get your first design of the network in, let's say, quicker than 10 minutes for a network of this size. And additionally, when you have your first design, you can quickly generate multiple scenarios. Again, it gives you another 10-15 minutes to calculate, but you have easily additional scenarios for comparison. So later on, I will show you a second scenario. So if we zoom in on those areas, we see here now the distribution network in zoomed fashion. Again, we're using here steel pipes, 10 bar, and the length of the distribution network here in this case is about close to 36 kilometers when looking at the street pipes. Then the last layer are the building connections or the service connections. So these are the interconnections from the pipes laid out in the street to the buildings. And also there we have a total network length of about 7.2 kilometers for these additional connections, which brings us to a total of about 50 kilometer network for this area. So this was a good indication for us to get an idea of how long the network would be. We can visualize the results in Google Earth to get an idea of how it would look like. we can zoom in, look at some details, maybe change a few parameters, maybe try to use other routes and fine-tune the design. And of course, a network of this size cannot be deployed in a year. It is huge. It's a big amount of work that has to be done. So we assumed here a rollout in a period of 7 years, starting in 2023 and finishing in 2029. So the clusters you see here again correspond with the building clusters. And what we have done here as an exercise is to assign a year of rollout to each of those clusters to have a phased rollout. So if we look what it would mean for the first phase in 2023, we get the network looking like this. And here we see the different steps, phase by phase, year by year, how the network could possibly grow and expand. Until we finish then in 2029. So in combination with the visuals, the tool also generates the individual costs for each of the phases, plus also the exact length of the pipes that you need in every phase. This is then shown here in this table. So you get the detailed view of all the equipment, the pipes which are required phase by phase. So as I mentioned, we have now generated one scenario, which took us, let's say, about 3-4 hours to set up. After the first calculation, which is there in about 10-15 minutes, we have now first design. And now we can go back on our steps, make some changes, and generate new designs. So by the time we finished the first scenario, we got new information, new data, which made us able to further refine the design. So the change that we have applied here is, first of all, that instead of using one source, we're now considering to use 4 different sources, to spread the power over 4 different sources. We keep using the same supply and return temperature. And we also got new information about deployment cost, as you will see in a minute. So this is the updated design. We have used here 4 different heat pumps near the river, and we have created 4 different clusters which are not interconnected with each other. We have, in every cluster, we try to get a kind of a main spine from the south to the north, and we branch off horizontally down the streets to enter with the pipes mainly from the back of the streets, from the back of the buildings. That was the main idea. So the tool is quite automatic, but it still gives you a lot of ways to control the routing. So there are still a lot of ways where you can steer the routing in this or another direction. When we look at the difference in length, we have a slightly shorter network length. We get about 46.6 kilometers here instead of the 50 kilometer as we had in the first design. And the heat pumps each have a power requirement of about 10 megawatt, which means cascading 2 units of about 5 megawatt each. So this is again the Google Earth view of this design. And as I mentioned, we got new information about deployment costs based on previous projects that have been developed in the area. The table is showing the price per meter for the different pipe types, and that includes different aspects. It includes the excavation cost, supply and return pipe, welding and installation, expansion loops and extra material if necessary, refill and repair the top layer, and project management overhead, so for a stretch of 1 meter network. Additionally, we have included the cost of the heat sources. We have an amount of about 4.5 million pounds per heat pump of 10 megawatts. We also have categorized different heat delivery units depending on the power, so up to 50 kilowatts, 3,000 pounds, up to 100 kilowatt, 10,000 pounds, etc. To give different types of heat delivery units depending on the energy consumption and the peak power of the buildings. And then this is the result we get. So for this area, we get a total project cost estimation of about 85 million pounds. That's on average 74,000 pounds per building, of which 82% is going to the distribution network and the sources, and the service connection and demand. Actually, the customer connections count for about 80% of the totals. So that is what we have been able to generate now with the tool. And I leave it up now to Ben to give some conclusions on the economical viability of this design.
Brilliant. Thanks very much, Kurt. Yeah, so let me just get this one over here. So as I sort of said at the beginning, this is a group of like-minded companies that are trying to, use their expertise, their knowledge to have a discussion. So part of what's been happening is we've had, iterative discussions with Kurt and his team talking about the variables and the factors that might need to be changed, and that sort of way of collaborating has been a really good way to get a feel for getting it more accurate. And we've got the likes of Vital Energy and IES who are also contributing to this work, and that invitation is open to the extent that we're very interested to hear what other people have to say about this. It's meant to be collaborative and open. So we will be adding more deployment cost information and better load modeling. Load modeling is going to be key to really refine this again. Should also mention we presented it to Glasgow City Council, and yeah, they were behind it insofar as that they liked it a lot, and they were very keen for us to carry on, and they were very happy to see it sort of following their own strategic direction as well. So yeah, it's all about getting as many people talking about these things as possible.
So Dave, if you could maybe come to the conclusions and share your thoughts about the results that we have achieved here.
Thanks, Kurt. A speedy run through, well done. I think the interesting thing for this is it's not the end of the story, it's the end of the first chapter. And as one of the slides said, we go back round. But just taking what 100 million is a round number from that means, when you work that out over 40 years, which district heating tends to have a long life of, you get a fairly low cost of the capex per kilowatt hour. So 200 gigawatt hours per year, and that depreciated cost over the piece is about 1.25 pence per kilowatt hour for the capex. The second area is what's the operating cost of this, and this is probably the biggest variance. When we look at the running cost of generating heat, it's entirely dependent on the cost of electricity. And electricity, as we know, is varying significantly in the UK. We're seeing periods of negative pricing at certain times, and we're seeing periods of relatively flat pricing. We're seeing periods of peak pricing. So absolutely the control technique is not to buy electricity when it's super expensive, which is between 4 and 7 in the evening. But that's just a thermal storage piece, and I've listened to Hendrik Lund for many years from Aalborg University, extolling the virtues of centralized heat storage being the lowest cost form of energy storage. Something like 1,000th of the cost of electric storage in a battery, a hot water tank essentially. So if we plan to buy our electricity as cheaply as we possibly can at say 6 pence per kilowatt hour, and that might need some private wire aspects to this, certainly easier in some cities other than Glasgow. It's quite far from where we're likely to see mass deployment of offshore wind, for example. But sticking with the theme, that would give you with an operating performance of the heat pumps of 3 to 1, which is okay. It's not fantastic, could be better, and that's where the strengths of Minibems come in to try and drive the network temperatures down. But that would give us a cost of producing heat of 2 pence per kilowatt hour. So straight away you're seeing costs for heat of somewhere between 3.5 or 3.25, sorry, pence per kilowatt hour and 4.25. Now the takeaway for this for me is that is not going to be cheaper than gas. There's a reality that gas at the moment is down around about 2.5 pence. So even with these sort of fairly broad assumptions about cost of capital and missing out a whole bunch of other costs, we're not getting close to the cost of heat. Now, before going terribly much further with this, what I would say is we need to strengthen the team of what we're doing, and two of the key areas that we've identified that we'd like better support from, which hasn't been fed into the model at the moment. I have to stress that. But the work that we've seen Vital Energy doing in district heating schemes around the country would appear to bring more accurate cost deployment information. The second piece of information, I first worked with IES. Glasgow University did a study with 2 students that I mentored, and using their software, they modelled the entire university to show what the heat demand for the university would be, and there was a pretty good correlation with reality. But we haven't used that type of modelling software, and I'd really like that to feature in the next phase of this work as we go back round and do it again. So I think the summary in all of this is simple economics isn't going to make this work. We need to get into some sort of surety of offtake to draw the funders into the scheme. But we've now got a framework of, you know, some sort of concept of what this would cost, and I think that's the key starting point to realise that you know, this is going to need a fairly strong hand from the city and from the government to make this work. So I'll hand back to Kurt to carry on with the final slides.
That's all panelists are welcome to reappear if you wish. I think that's. We can move on to questions. We've got a few questions coming through already. Just for completeness sake, I'm gonna launch the second poll, which is same as the first. It would be really good to see what your points of view are, everybody. If you could just quickly answer that one again and just let us know what your thoughts are in terms of whether you now believe it is more or less achievable to deploy heat networks in cities. That'd be great. I had a pretty positive point of view at the beginning. Let's hope that we've not dissuaded people. Okay, I'll close it there. Thanks very much, everyone. And okay, looks like we've possibly delivered a little bit more certainty, a bit more information. But yes, there's lots of questions that we need to look at. So let's have a look. Let's go to the questions and see what is on your minds. Okay, the first question from Roddy Yar. Thanks for joining us, Roddy. The question is, does the 200 gigawatt hour include the universities, college campuses, communities of Carlton, Gorbals, Drygate, Townhead, and the hospital? So we talked about having a 200 gigawatt hour total heat demand across our heat network section that we've selected. Does that include all these different aspects? That's local knowledge, isn't it, Dave? I don't think.
So I would answer simply then pass to Kurt, but it doesn't include anything to the east of High Street, which would rule out some of the Drygate area and the hospital. And I don't believe it includes Strathclyde University, which we drew a box around because the district heat network has already been successfully deployed there. Of course, it could be connected as an auxiliary source. So Kurt, I don't recall if from the slides whether it went as far north as the other university in the north of Glasgow, the Glasgow Caledonian.
Oh, you're on mute, Kurt.
Right. So it's correct. The university area is not included, but I have to say, of course, that this information is based on the extracts of alt maps. Of course, it's not 100% accurate either, but it's a good first estimate for the full area. Let's say we have to take it at least with an error of plus minus 10–15%, and then a further detailed study. We will need a detailed survey, like I mentioned in the introduction as well, of course.
Certainly, yeah, and the Gorbals aren't included, are they? Because that's on the south side, so it's everything north of the Clyde.
North of the Clyde River, yes.
Yeah. Okay. And a follow-up question there from or comment from Roddy. Deployment would be best organised along with other urban realm infrastructure works, i.e., the Avenues programme Dig Once. Definitely, I think if everyone's in favour of heat networks, they're even more in favour of not having to dig up the roads.
Yeah, it reminds me of the phrase, why change the habit of a lifetime? Why not dig the roads up and then go back 6 months later and dig them up again? No, because it's a really bad thing. So absolutely, this is a huge opportunity, you know, and what I've seen of the software is really powerful. You can force it in different ways. Kurt didn't mention some of the bit about the main spine. We took a very simplistic view of how to run them up the quieter streets from the Broomielaw up the river northwards in each case where we possibly could, but equally we could force it to say, well, let's go up this road because that's prime cycle path area, and force a dual solution so that we finish off with some nice green tarmac and some bollards. Absolutely.
Okay. So next question. How do the maintenance, this is from Andy Davey, thanks for joining us, Andy. How do the maintenance costs of the heat pump compare to maintenance costs of gas boilers or gas CHP, you know, perhaps expressed as £1 per megawatt installed?
I'll answer that. Higher than gas boilers, but then it depends how many gas boilers and who's actually doing the maintenance. We take a figure, it's a rough rule of thumb that works for smaller systems, of around about 4 to 6% per annum maintenance, but that's to make the plant last well beyond 20 years. So there's the other aspect of the REPEX cost, which comes into it. So we've got industrial refrigeration plant that's now over 30 years. Interesting thing with gas CHP is you probably have to replace it after 15 years. So it's exactly the sort of question that feeds back into another pass at this whole theme to try and get it more accurate. But you know, maintenance quite clearly gets cheaper as plant gets more consolidated. I think this draws an interesting question about dispersed heat pumps in every building versus centralized. The other key aspect of this is, of course, we're using natural working fluids, which aren't going to be phased out, and so the plant should be running 30 years from when it's deployed without having to be changed because of CFCs or cousins of CFCs, as we're now into in some of the more exotic fluids. You know, every decade, every 2 decades, we've seen plant being changed because the working fluid is no longer acceptable for a new reason. Ammonia has been used since 1860 or so. It's the only working fluid in continuous use since the beginning of industrial refrigeration. I think that's an interesting stat just to keep in mind. It'll probably prompt some questions, I'm sure, that aren't really a topic for today, but I'll leave it as we've got ammonia plant in the roof of Great Ormond Street Hospital. So if you can do it there, you can do it pretty much anywhere.
Okay, thanks for that, Dave. Yeah, just a follow-up question from Andy is, how many times would the heat pump need to be replaced across a 40-year district heat network scheme lifetime?
Well, there's an element of triggers broom if anybody's a fan of Only Fools and Horses, and you can change all the bits, but it's still the same heat pump. But joking aside, the wearing part of a heat pump is a bit comparable to the engine in a car, if you like. It's a small part that's the compressor, and that's the bit that you might change. The heat exchangers and the pipes and so on should still be there, you know, for 40 years. You know, it's not rusting from the inside, that's for sure. So that gives you a very small amount of replacement parts. Again, and it's not intended to be one versus the other, but drawing an obvious comparison with a gas engine, a gas CHP, when the gas engine, the entirety of the block is the gas engine. So when that bit has to be replaced, the entirety pretty much comes out. With the heat pump, it's the compressor in the middle that one might take away. And obviously, because of the relative size, there's a relative cost advantage of that. So we wouldn't be expecting parts of this to last years, but equally we would expect the bulk of it to last 40 years.
Okay, there's a bunch of questions from you know, lots of you guys regarding the modelling. There's some sort of technical questions. There's more financial questions. So I'll try and sort of bunch together a series of questions that are more technical. Peter Spurway says, fantastic software and exciting project. Has a scenario been run for a 5th generation network across the city? And how would the lower flow temperature affect cost modelling, take into account larger pipe?
Well, a lower temperature would not necessarily mean that there will be a bigger pipe requirement. So it's the delta T that will determine the pipe diameter. So if you work with an 80-50 network, or if you work with a 50-20 network, we have the same delta T of 30 degrees, so the pipe size would be identical. But if you further lower the supply temperature, then we might need heat pumps inside the buildings to increase the temperature for, let's say, 40 degrees, maybe up to 60 or 70 degrees. So that would require an additional heat pumps in the customer buildings. So, and yeah, so no scenario has been run for a 5th generation network. I mean, we're now moving with the software towards features of 4th generation networks. I believe we talk about 5th generation networks. You have multiple sources, heat, cold, exchanging heat and cold, using heat pumps. So that is not yet taken into account into the study now.
Okay, good stuff.
I'd add to that, it could be, I mean, this is another go back around the loop, but ambient networks that we're seeing are on a delta of maybe 10 Kelvin. So you're talking about 3 times the flow rate. That quite clearly is something that has to be looked at and modelled, and the software from what I've seen would allow that repeat to be done. But basically it puts all the pipe sizes up. The interesting thing about pipe sizing is the trench cost is a large part of the cost. So making pipes plastic and uninsulated doesn't make a massive difference to the overall cost of the trenching. Pipe getting bigger, but uninsulated, there's a trade-off with that. But that's exactly what ComSoft can do when you go back around the loop and do it again. But it's a very good question. I think from the starting point of what do you end up with? You end up with a situation where you've then got potentially 1,000 heat pumps round about the individual buildings instead of 4. And that's quite clearly different. I think the point I would make about that is when we're looking at the running cost of this network, it's fundamentally about the cost of electricity. And the cost of electricity varies for lots of reasons, but one of them is how centralized your procurement of that is. If you can buy it in bigger chunks centrally, it's likely to be a lower price. And certainly if we take the absolute extreme of that, of private wire, I mean, this would suit a city like Dundee very well, where the North Sea areas where they're rolling out offshore wind, private wire direct into the heat hubs at the banks of the Tay in Dundee. That's absolutely going to be a lower cost of electricity than trying to do private wire into 1,000 different buildings in the city centre. It's just not possible. So you'd have to be buying from the grid, and it takes you into a whole realm of questions around grid infrastructure, etc., etc. So it's a really good question that prompts a complete review of the whole piece. But I suspect one will want to run these systems with the lowest possible cost of electricity purchase, because that is the dominant number in the output cost of heat, and that's what we're aiming at, the lowest possible cost of heat. So the gap versus gas is the minimum possible, so that there's the maximum chance of influencing people to move from gas to district heating, because the price difference is as narrow as possible.
Okay.
I presume also that the design at the moment doesn't take into account upgrading all the internal systems for lower flow temperatures. So you're using the existing radiator systems, etc. On that basis, Dave, are there advantages in terms of COP when you've got a single heat pump doing high temperatures that you're suggesting there, versus smaller heat pumps that may be able to achieve 80 degrees but maybe at lower COPs? Is that a factor?
There's several sort of levers moving in different directions. 80/50 it's not a very good district heating network. It has to be said. We should aspire for it to be better. But I would make the point that even if we installed the 80/50, for example, and then started applying the skills of Minibems to manipulate the way that the buildings actually consume heat. And let's keep it at absolute basics. The buildings are wanting rooms at 21 degrees and hot water if they're storing it above 60. So 80 is a bit of an overshoot in that. So I'm certain we can get the temperatures down. 80 comes about from trying to keep return temperatures at 70 plus to not get condensation in boiler flues and so on. So there's an artificial starting point. What I don't immediately jump to is that you should try and rip out the internals of every building. Think about the customer mindset. If you're the Hilton Hotel in Glasgow, for example, and I knock on your door and say, hey, would you like district heating? We're going to do this wonderful thing at 60 degrees, but you're going to have to change the internals of your building. The chances are that the client's going to say, well, I don't really fancy that.
No, I agree, Dave. I suppose my question was more on the ambient. I was still on the ambient thing. If you work on the basis that you're going to need, at least from a peak load design point of view, you're going to need those high flow temperatures for peak loads. Yeah. Is using 1,000 heat pumps, as you say, feasible? Given that do you get a different kind of characteristic COP out of the smaller type of unit with different refrigerants and different technology than you do out of your sort of ammonia-based, large scale heat pump at those temperatures? Yeah. A
straight two numbers. One is, as you lower the flow temperature, the COP improves by 1.5%. So even changing from 80 to 70, 15% better. Changing from one working fluid to another gives you a change as well. So an ammonia heat pump of say 500 kilowatts will be about 15% better efficiency than an HFC heat pump of a similar operating temperature. So as you change from one system to the other, you're doing two things. One is changing the temperature, and the other is changing the working fluid. And there's a trade-off for it, and you've got to balance it. I think the reality is that we've got to get something that's workable as quickly as possible and doable and rolled out as fast as possible. So I think it comes back to the sort of customer sort of inclination to do one solution rather than the other solution. It's about making it easy for people when you knock on the door and saying, I want to completely take you to a new paradigm of how you heat your building. You've got a relatively complicated option of change your building internals, have this new device, upgrade your power supply, or look, plug into this HIU that's got everything done for you, the other side of the demarcation line. That's the sort of thing. So efficiency is going to come into it, but if we change the efficiency by 10 or 15%, it clearly affects the numbers, but not so much that you would say, I'm not going to do that. I'm just going to keep burning gas. We've got to move forwards, not keep sort of pondering which way to go. And that's the really tough thing. That's the whole purpose of this exercise, is to try and give an insight of which direction to go in. I genuinely sit in the fence of centralized heat generation to relatively high temperatures. I always want it to be as low as possible, but 80 for the sake of argument, but I'd prefer it if it was 70, and I'd prefer it again if it was 65 or 60, or some sort of ambient network. It's getting a lot of chat around. There's some really fantastic projects, but is it the right way to go for this? You need to do the modelling and see what it means. See what it means for the network costs. See what it means for the dispersed cost of heat pumps. Certainly, heat pumps get cheaper as they get bigger. That's another factor. So you've also got the diversity. We've managed to with about 40 megawatts, cover that city centre area. If you had a heat pump in every single building, you've totally lost the diversity factor. So each heat pump has to be sized for the peak of that building. So that pretty much, all sorts of stats around that, but it probably puts the capacity of heat pumps installed up by a factor of 2. So it's complicated. I can't give a simple answer.
Yeah. No, jolly good. Just to continue just a little bit the theme of 5G, a couple more points coming first from Peter Dunsby, and then next from Tony Amos. Thanks, guys. Peter says some buildings will need 80-degree centigrade heat, but you can also get the benefits of a 5G network and recover heat from other available heat sources. Separate pipework, same route, asks Peter. And Tony asks, will the heat network deliver cooling as well? Same sort of theme. There will be many buildings with data centers, servers requiring cooling, which would help in the overall economics. Unless you've got specific points you want to address there, guys, I'll just move on to another couple of questions.
I think it's worth pointing out, Ben, that you know, this is a voluntary consortium of stakeholders at this stage, and that, you know, there is no government behind this vision or this idea. Just to put some context around what's going on here for people.
Sure.
Yeah.
Cool.
I think, Ben, just to say something about the cooling, but the cooling is not included in this, and there definitely are demands for cooling in any city where they're doing things. I think some of them are artificial, to be perfectly honest, where we're opting to use forced mechanical cooling when we could use a bit of ventilation. So I wouldn't immediately jump to the amount of cooling we're doing now being right. Equally, you know, as climate change arises, we're likely to see more demand for cooling. So that's a factor in this as well.
Yeah.
It's been modelled on a 2-pipe heating system that doesn't include cooling. It is the single largest advantage I can see of ambient networks, that you can be putting heat in. But I would then say, why would you do that if you've got 200 gigawatts of heat available running through the centre of the city from the river? It's for places where it might be more appropriate, for example, for Birmingham, which doesn't have the same access to its own ambient source. The canals are relatively tiny. You might get a megawatt from a canal. So horses for courses. Key thing to put it back in as you go back around the loop and reconsider. Absolutely, I'm not dismissing it. I'm just saying it's there's quite a bit to it.
Okay, a couple of questions about just the inputs we put into the model that I'll address to Kurt. One from John Mitchinson and another from Jorn Miras. Thank you both for your questions. John asks, could installing polymer pipes for distribution of heat lower the overall cost? And Jorn asks, for the per meter pipework network cost, are surrounding parameters like road type and traffic density considered?
Okay, so the first question was if polymer pipes could be installed instead of steel pipes, and if they would reduce costs. Well, there is indeed a slight impact on the cost, but as Dave said earlier, let's say if we look at the total cost per meter of a network, I believe that only between 15 and 20% will account for the material cost, and about 80% will account for the trenching cost, the installation, the overhead, the repair of top layers. So the trenching is the main driver of the deployment cost. And choosing for a polymer instead of steel will only have a slight impact on the overall cost. And the second question was about the meter. What can you repeat the second question? The cost per meter?
It was parameters like road type and traffic density, whether those types of factors have been included in the per meter pipe network cost.
Right. Well, the costs that we have used now are based on previous projects that have been run in the area of Glasgow as well. So I don't have access to the source of the data, but it has been used in previous projects in the area of Glasgow. So I don't know if Dave, if you can comment about the source of the costs, but they are totally valid for the Glasgow area.
Yeah, it's a really good question, and it's a shame the slide's not on the screen, but what the east-west lines that we use, particularly in the furthest west zone, it wasn't obvious from the resolution of the plot, but they actually are planned to run up and down the lanes rather than up and down the streets. So, around the area of Blythe Square, for example, wherever possible, and this is the power of the software, is that you can take a road and say, don't go there at all, or don't cross it, or if you are going there, let's just say it's a mega busy junction, you could say let's apply a cost per metre of £10,000 to that bit to force the software around it effectively. So the question is really valid, and it's the bit that really struck me about the modelling, is that you have to bring some local knowledge to this. Now, I've tried to do that, as lived in Glasgow most of my life, and can tell you which streets are busier and which have got the buses and which don't. It comes back to Roddy R's comment about routing and where to put stuff. Do you want it in the bike path or not, and all the rest of it. When you do this modelling, the key thing is you can keep doing it. Once you've got the basis set up, you can keep doing it to try and improve it. So you absolutely want to avoid Hope Street where the buses run up. That's one of the busiest streets in Glasgow. So you'll go one block to the west and you find a much quieter street. And don't run in the east-west traffic arteries. Run in the lane. So we've tried to, in a sort of, as Vinny said, this is a bunch of geeks having a shot at this. Free of charge as a first pass to try and inspire people to use this. The key thing is this is the methodology that needs to be applied with better inputs, but it's the right methodology as you go back around the buoy again and have another go. So,
okay, listen, we'll carry on with a few more questions. People may have to leave, but James Little and Carlos Rodriguez have also been in touch. Thanks for joining us, gents. James asks, have future gas costs been modelled? With no new buildings being connected to gas from 2025 and likely future carbon taxes, the 2.5p per kilowatt hour average is likely to rise. I guess that's for gas. Also, this project would be eligible for HNIP funding. Any comments on the gas costs?
He's absolutely right, and equally, are we genuinely going to see the cost of gas rising? I think that's the elephant in the room. The counterfactual of cheap gas, and there's data. It's a while since I looked at it. It was back in the days of DEC, but there's a graph showing that gas is going to be cheap forever, pretty much. So that is not compatible with decarbonising a city. So we're going to have to put some downward pressure. Personally, I would start looking at things like air quality. It's very topical at the moment with the improvements we've seen during the current COVID-19 crisis, but I would start saying to buildings, it's really not acceptable that you produce the level of NOx emissions by burning gas in the city centre that you do. If we're going to see by 2030, and this is not my target, it's 2030 is what Glasgow and Edinburgh and other cities have said of the target. If we're going to see near completion of this challenge, we've got to do something fairly radical fairly quickly. What rules are available to us? We've got to drive down the emissions. That's effectively what it's about. So I would be concentrating on driving down the stats go by cost. Gas price, climate change levy applies, but not very much. It's 6 times as punitive on the use of electricity per tonne of carbon as it is on gas. That's clearly just a bit of a mistake. So if you balance these things up, you start seeing the counterfactual coming up, and it will have to. We've got to get the gap narrower. But I think from our basic first pass, we can see we are not going to roll out district heating networks and say to people, this will be half the price of burning gas. So there's clearly got to be some other influencing factors.
I think if nothing else, in a way, developing this scheme and developing some sort of vision, if nothing else, just demonstrates that the gap in the gap in funding that actually exists, the level of investment in infrastructure investment that's required to decarbonize cities, it's not going to happen through market economics, is it? And this project nicely demonstrates that, and is something that maybe can be used to give to policymakers, etc., to try and demonstrate, just how short the shortfall that exists in funding, but also probably the perception of what needs to happen.
Yeah. Okay, Carlos Rodriguez, just to refer to his technical question, in the multiple heat pump scenario, how the cold water discharge of the heat pumps is achieved not to affect the efficiency of a heat pump located downstream. I guess there's sufficient flow at the river for that not to be an issue.
I think he's maybe asking about a network where you have a single pipe ambient loop. where a building on an ambient loop that was say going from 15 down to 10, one building takes some 15 water, puts it back into the same pipe, so the pipe then becomes 14.9 degrees because the flow rate's relatively big. It's a completely different format. This is one of the challenges. You've got two pipe hot, you've got four pipe that's too cold and too hot, you've got twin pipe ambient network at say 1510, and then some people advocate single pipe loops. I think what Kurt's analysis shows is a city is a very complicated place. You've got to assume that you can model it to a very good degree, but there's still going to be things that aren't quite right. For me, the single sort of feature to remember is you've got to design for the peak day. That day when it's -5, all these buildings want that amount of heat. If they're all taking heat out of an ambient network, then the network has to be sized for that. It's this balancing thing it kind of works in some of the schemes that have been done. I was very inspired when I visited here, Len, in the Netherlands, but it's a completely different basis of city. It's not quite the same comparison.
Carlos basically adds a wee comment just now saying he meant that he would, that we'd be cooling the river source.
Apologies. Well, Carlos was quite heavily involved in the design of Queen's Quay down at Clydebank. Did some good stuff down there. We're cooling the river water that we extract by 3 degrees, and if we're taking 40 megawatts out of 200 gigawatt to 200 megawatt supply, the temperature change is tiny compared to what's permissible by the Environment Agency. So even the cities in Gothenburg, Sweden, that have got 160 megawatt heat pumps taking heat from the sea and from the river. So you've definitely got to monitor these things, but the quantity of heat that's being taken from the river is tiny. This is a stream that is flowing from the upper reaches of the Clyde Valley. It's a 4,000 square kilometre solar collector over the course of the year that's feeding by gravity into the centre of the city. So big source, tiny extraction.
Yeah. Okay. Well, we're past 10. There's a lot of other comments that have come through. Just to summarise a couple of things, Catherine Cooper has been in touch with a number of comments just regarding the fact that actually a lot of work has been done out there. There's things happening in Dundee. Sustainable Glasgow team have done lots of interesting work in terms of load requirements. Dunfermline, vital scheme in Dunfermline would be a good benchmark to look at. So thanks for all those comments, Catherine. And I think your main point is we need to sort of bring everyone together so that we're not duplicating work and we're actually moving this forward. So indeed, that's a real part and goal of what we're doing in these webinars, to try and get people tied in together so we can start deploying and making things happen as quickly as possible. Roddy Yar mentions that we've got 4 gigawatts of onshore wind potential south and southeast of Glasgow. 40-year concession and the contract for difference may bring these developments forward. So it would be great to tap into that electrical source for heat pumps. Greg Davidson makes a good point. Living in a city centre tenement, one aspect that has been glossed over is the technical challenge of building connections. Running pipes externally will be a non-starter due to planning conditions. Who will cover the cost of the internal building modifications required? So that there is clearly there's a job of work that needs to be done inside each building as well, and we've accounted for the connection into each building, but then there's the sort of pipe work and plumbing that needs to be done within each building.
I think that, well, there's several parts to this question. It's a good question. It's, I think, one of the hardest bits. Doing a big office building in the centre of Glasgow is a single connection for quite a big heat demand, and the key number in all of this is how many kilowatt hours per annum do you sell per metre of pipe. That's the ratio you're trying to get. Tenement buildings, really tricky, really hard to do. Might not suit this district heating approach. Might be one of the areas that's best done by a different technique, whatever that comes to be. Planning is clearly part of it. I think what I would say that running at the back of the buildings is probably easier than running at the front of the buildings. The key thing about what we're trying to do with this higher temperature network is you should make the modifications inside the individual apartments as limited as possible. It's a gas boiler off the wall and a heat interface unit that would be smaller onto the wall. So there's a fairly simple answer for inside the apartments, but how do you get the pipes to each individual flat in Novar Drive, for example, in the west end of Glasgow? The short answer is you have to run the pipes up the wall, but they might, if they're the right colour, look like a drain pipe. So we perhaps have to just crack on and get on with this, and you know, try and keep the fronts of the buildings as untouched, but the backs of the buildings have got all sorts of stuff going on with TV aerials and satellite dishes and all the rest of it. You know, is it nice looking out the back window and seeing plumes of steam coming off the individual apartments? Probably not. So I think there's always a trade and a balance, but he picks up on one of the hardest bits of Glasgow of how to do it. I did see a scheme in Stoke that was talked about running the pipes along the buildings above door level and below window level. There's also been some suggestions that running in roof spaces in tenement buildings is a viable option as well for these final leg of the spine. So again, we have had a first pass at this to promote discussion, which is great. You're getting the questions here. That is a really key question of each individual building. How are you going to do it? We've got to do something.
Yeah. Now listen, there's been lots of other comments. Thanks very much for everyone who's sort of thanked us for it. Who have a number of people saying that, you know, it's really good to have a debate and to sort of start here with these sorts of ideas. So thanks for those points of view. John Mitchinson, you asked a question about what is the cost per ton of carbon dioxide saved, and it's about your guesstimate was around £2,000, and from the numbers that we looked at yesterday, I think we said it was about 45,000 tons, a best case scenario of CO2 saved over the lifetime, Dave.
I think if you go back to one of the slides, it was kind of there, but this is a key question. You know, when we're deploying electric heat pumps, what is the carbon footprint of that? Is it the grid average? Is it incremental carbon factor? Is it fat end of zero because we've got more electricity we need? If we've got a private wire from a new wind farm somewhere, then surely that's not got to be taken as the grid average. So that's a key input to this. I think you've also got to look at deployment cost and what that actually is. The interesting thing about the analysis Kurt's done is that it shows that deployment cost, digging up the streets, is the key bit. So what is the exchequer tax take from creating all these jobs, digging up the streets? You know, a pound spent is something like 70% gained by the time you work through various permutations. So it's an interesting thing about the modelling, financial and carbon modelling is probably not a feature of what we've done to date, but if there's an expert out there that thinks that they are the dude for that, then you know, get in touch, join the mission. There's no money in it, but join the mission.
Nice one. Listen, I think we'll leave it at that. That was a really lots of good points there. I've got a copy of the questions so I can share them around if anyone wants to have a look. There will be a recording of this next week, and the slides are available for those who want it. We've not had a chance to really go into this, but there you are. That's Comsoft Reference has done a lot of work, including the Port of Rotterdam, so some good track record there. And there's contact details for Kurt and the website. And as usual, if there's any projects that you'd like to discuss with us regarding existing or new heat networks, you can get in touch with Finn. There's the email. And if you're interested in taking part or doing some co-marketing of some kind, then you're very welcome to me a line and we can talk about doing a webinar. The next webinar won't be for a couple of weeks. And that's going to be a Minibems focused series, and that's going to be talking about how we can convert existing heat networks in the UK to a high performance service. 500,000 connections out there that are neither metered nor controlled. 300,000, and there's a big opportunity at a relatively low cost to reduce carbon, improve performance, and give heat networks a good name. Thanks very much, everyone. Thanks a lot to Kurt. Thanks, Dave. Thanks, Finn. And we'll see you next time. Thanks a lot.
Thank you. Bye.